In this video, I'll be demonstrating how to insert a Faraday isolator into a laser beam in free space. The Faraday isolator consists of three parts: an incoming polarizing beam splitting cube, a Faraday rotator, and an outgoing polarizing beam splitting cube. Linearly polarized light incident on the incoming polarizing beam splitting cube such that the angle of polarization coincides with the angle of transmission of the polarizing beam splitting cube will be transmitted through the polarizing beam splitting cube. It will then have its angle of polarization rotated by the Faraday rotator such that it emerges from the Faraday rotator with an angle of polarization 45 degrees to the original angle of polarization. It will next be transmitted through the outgoing polarizing beam splitting cube, whose angle of transmission is 45 degrees with respect to the incoming polarizing beam splitting cube. Light going the opposite direction will be sent through the outgoing polarizing beam splitting cube and it will emerge with a linear polarization 45 degree angle with respect to the incoming polarizing beam splitting cube. The Faraday rotator will then rotate the angle of polarization such that it's 90 degrees with respect to the transmission angle of the polarizing beam splitting cube, and it will be sent out the side. Hence, the Faraday rotator prevents backwards flow of light. The procedure consists of 4 steps. The first step is to insert and align the Faraday rotator. The next step is to insert and adjust the incoming polarizing beam splitting cube. The third step is to insert and adjust the outgoing polarizing beam splitting cube. And the fourth step is to adjust the Faraday rotator using an adjustment knob to adjust it for the wavelength of light being used. The Faraday rotator uses a fixed magnet, so when sitting down on the optical table, it'll be drawn to the optical table, so be careful. Prior to this demonstration, I set up a laser beam in free space with 2 mirrors such that after the 2 mirrors, the laser beam is parallel to the optical table and runs with the holes of the optical table. This will make alignment slightly easier. I'll be using a technique to adjust the outgoing angle of the laser beam such that it coincides with the Faraday isolator. And the technique is known as walking the beam. This will require 2 mirrors where you adjust the angle of one mirror and compensate with the angle of the other mirror. This is done with both the horizontal and the vertical angles. To get a better idea and understanding of the walking the beam technique, you can view one of the other videos where I couple light from an open beam in free space into an optical fiber. Okay, so the first step is to insert the Faraday rotator. So I'm going to remove the 2 polarizing beam splitting cubes and then insert the Faraday rotator into the beam. Now to view the beam, I'll be using a near-infrared viewing card because our beam is in the near-infrared wavelength. So we can just start off by visually inserting this. Alright, so I'll move the horizontal position and then I'll lightly clamp it to the table so I can adjust the vertical position. Alright, so I need to adjust the vertical. It looks like it needs to come down just slightly. There you go. Alright, look at it. So the beam is emerging from the Faraday isolator. So now we have 2 things that we can check. We can check using a power meter the incoming power versus the outgoing power. We can also check using our card a visual representation of the beam. So we can look at the beam shape going in and the beam shape going out. Alright, so I zoomed in so the camera can see both the incoming and outgoing beam so we can compare the shapes. So if we look at the incoming beam, we can see it's quite round. Compare that to the outgoing beam, we can see that it's not quite round and it's scattering light a little bit over here. So what I'm going to do is I'm going to change the angle of the Faraday isolator or Faraday rotator to see if we can have a better alignment. Alright, so it seems to be improving. Alright, so I changed the angle slightly and we can see that there's a nice round beam coming out pair along with the round beam going in. So now we can use the power meter to do a second check. Alright, now we can check the incoming power. Let's see, and we're here about 9 milliwatts. We can take a look at the outgoing power. Alright, and it's about 7.51, so I'm just going to use this mirror and adjust the angle to maximize this. Alright. Alright, so it looks like we're around 9 milliwatts, saying just the vertical angle now. Alright, so I think it's good enough to move on to the next step. And since we adjusted the angle, I'm going to take one last look at the beam, make sure it's still nice and round. Alright, so the next step is to insert the polarizing beam splitter, the input polarizing beam splitter. So I can put it in here, and now I just need to rotate it to maximize the outgoing power. So I'm going to rotate it, and it seems like it maximizes around 8.2 milliwatts maybe. Yeah, 0.2 or so. So I'm going to secure it. Alright, so again, it slightly changes the trajectory, so we can use this mirror to align it again. Alright. But at this point, this is not too critical. Alright, so now the next step is to put in the second polarizing beam splitting cube. So I'll insert it, and then I'll put the power meter in front of it. And now we can turn this to maximize the output. Alright, so it looks like about 8 milliwatts. There we go. Secure it down. And I can adjust this if I like, but let's see, I'll adjust it slightly. Alright. But I'm not going to put too much effort into this because the next part is to do the fine adjustment, and for the fine adjustment we have to turn the whole Faraday isolator around and measure the extinction. So I'm going to turn it around, and then quickly realign it. So here we go. Take a look at the power coming out. So we can barely see the power going out, so that's good. We'll put the power meter in front of that. I have to adjust the scale on the power meter. So I'll adjust the scale, there we go. So now I'm going to turn this adjustment to find a minimum. So it looks like it's maximizing it, so I'm going to go the other direction to minimize it. There we go. There you go, looks good. Alright, so I found a minimum. So now I'm going to turn it back around and then finally align everything. Alright, so put it back in the path, and I might have raised it a little bit while I turned it around. Alright, take a look at it now. Alright, so now I'm going to put the power meter in front of it, and then now I'm going to do the walking the beam procedure. So I'll readjust the scale on this again. So alright, so now I'm just finishing the walking the beam procedure. As you can see, you change one mirror and then compensate with the other to maximize the throughput. We seem to be reaching a maximum of around 8.5 milliwatts or so. Alright, so yeah, 8.5 milliwatts. The input power is around 9 milliwatts and the transmission is around 8.5 milliwatts. This is about 90% transmission, which matches the specs for this particular optical isolator, which is about 90% transmission, so we're good right now. And now we'll move on and analyze the extinction ratio. Alright, so the final part of this demonstration is to measure the extinction ratio, or I guess you can call it the isolation, the effectiveness of this isolator. Alright, so for this measurement, I again turned the isolator back around, so we're sending light in through the opposite direction of flow of the isolator. And I optimized the beam path of light by walking the beam using these two mirrors such that it flows optimally through the isolator. Furthermore, I manipulated the polarization of the light such that it's linearly polarized and its angle coincides with the transmission angle of this polarizing beam splitting cube. That way we get the maximum transmission through this cube. So we can take a look at the incoming power, and it's about 9.86 milliwatts, and compare that to the power sent through the isolator. We have to change the scale on this. It's about 4.7 microwatts. So that's around 33 decibels, which is consistent with the specs of this particular isolator. One other thing I'd like to note is that during this fine-tuning phase, or fine-tuning step, where we use this knob to change the wavelength tuning of the isolator, you can also change a little bit the angle of this polarizing beam splitting cube. You have about 1 or 2 degrees that you can change it, just to tweak it if you like to. In our demonstration, we didn't have to. Right, I hope you found this demonstration useful. Again, I'd like to point out that in the other video where I couple a laser beam in free space into an optical fiber, there's a much more detailed description of the walking beam procedure. So if you need more information on that, you can watch that video. And thank you for watching this video.